where we can address some popular statistical questions and put things into context. In a lot of circumstances, we can see a situation where we want to see if there's a meaningful difference between two variables or if two variables are related in some way. That's quite often the big question. What we also want to do is to look at the size of either the difference or the relationship between two variables. So over the next few minutes, we're going to have a look at a really simple data set and use that data set to look at how we can combine different types of variable to look at differences between groups and very specific relationships. Now we got the visual representations there to help us form meaningful inferences from the data. So in our example, let's say we want to measure the height of people living in a certain country. So we can't measure the height of everyone in that country, so we take a random sample. And let's say we measure the height, and we also measure some other information like weight, gender, some other characteristics of these people. And we arrange this into a spreadsheet. All pretty routine stuff so far. Now, everything that we would arrange into a column in this spreadsheet we could call a variable. Now, with most data sets that you work with, it'll contain at least two different types of variable. On some occasions, you'll encounter what's called a categorical variable, where you arrange characteristics of the population into categories, and in other circumstances we can have quite often called numerical variables, where we basically, or sometimes called continuous, where we can arrange them along a line in terms of small to large in terms of their magnitude. So with categorical data we can sum up or observe the frequency with which certain characteristics occur, and we can summarize this in a table such as we can see here. Whereas with the numerical data we can use the range, we can use the interquartile range, which is where we take sort of 25% of the data from smallest to largest value. We can use the median and we can use the mean. And the way we take this numerical data and visualize it is with a box plot. So that gives us the interquartile range, the median, and of course we can also use a histogram, which gives us a shape of the data. So hopefully you're getting an idea of how we can take numerical values, which as humans don't give us a lot that is very meaningful. But when we visualize that data, we can understand it a lot better. So let's say we start looking at combinations of variables. So far we can take an example of a categorical and a numeric variable. So let's take gender and height. So we can see that the summary of the numeric variable in either category is 1.58 and 1.54. So you can see that there's a difference there. Now, as you can imagine, there are other possible combinations of variables that we could look at. We've looked at height and weight, which are both numeric variables. In this case, we could look at gender, male and female, and height to look at differences, and we could also look at relationships. So in each one of these cases, we can apply statistical tests to quantify the size of the difference. And the key thing about statistics is that the whole reason we carry them out is to make inferences about the population of interest from our study sample. So at this point, it's worth pointing out that it's not a good idea to, as we go along, just amend our statistical tests just to try and find something. That's considered bad science. We should always do it in a particular order. So we come up with a question and the hypothesis, then define the null hypothesis and the alpha value, which you typically know as 5%. And all of this should be decided upon a priori, which means prior to. Let's say we want to analyze some data and just use one variable. So a question could be, is there a difference in the number of men and women in the population? Really simple question. So is there a difference? That would be our hypothesis, that there is a significant difference between the number of men and women in a population. Now, if we were to visualize this, we might see that there is a large difference. But remember, that could be just due to chance, because it could be that we've just recruited a sample where there's a lot of men and not many females. So we've got to try and disprove our null hypothesis. That's the way hypothesis testing works. It's a more robust way of carrying out research. So if you want to test the size of the difference, we could test our degree of confidence in that the null hypothesis is disproved and calculate the probability. But we must be clear about how small is small enough. We know what value of p value would we reject the null hypothesis. So we typically take that p value as 0.05 or 5% as the often called the alpha value of 5%. And so in a scenario where we've got p-value of less than 0.05, so when we do a one sampled proportion test, then in those circumstances we can reject our null hypothesis and see how, due to statistics, we can now say that the difference between males and females was not just due to chance. So another question, does the proportion of males and females differ across age groups? So we've added another variable here. We've got a dependent variable. So differences in numbers of men and women, does it depend on age category in our sample? If we just visualize this, we can see that, yeah, it does. In our sample, it does depend on age category, far more female children compared to older age groups. Now, is that just due to chance? Well, let's test the idea that the proportions are all the same, independent of age category. So that would be the null hypothesis. So we need to test this. So if the test that we carry out in this example, because we've got a categorical variable, it would be a chi-squared test. And then if our alpha is less than 0.05, we reject the null hypothesis. Now, if we want to just look at one numerical value on its own, now that is a possible scenario. So we might want to compare our data to historical data. So An extreme example might be to compare height today to height in medieval times, for example. So to do that, we would need some historical data to compare ours to. So is the average height different from a previously established height? God, it's painful. So we could look at another question and introduce another variable to see if there's a difference in height between men and women. So our hypothesis would be that there is a difference, and we can see that if we just chart our data. Our null hypothesis would be that there isn't a difference. So let's assume that there's no difference. So if we conduct a t-test, which gives us a p-value of less than the alpha, which is 0.05, then we would, really simple stuff, when we would reject our null hypothesis. So really straightforward. Now, if it was more than two groups, instead of a t-test, we would obviously do an analysis of variance. So here we could pose a question, is there a relationship between height and weight? So something you'd be familiar with, you've done before, is that when you're doing a correlation coefficient, you're looking for a relationship between two numeric variables, and you can see that if we slide the slide over to the left hand side, we've got a strong negative, perfectly negatively correlated, which in the real world we very rarely, if ever, get. And if there's no relationship, then the correlation coefficient will be 0, and then we go up to a strong positive would be 0.789, and again, rarely in the real world do we have a positive correlation of 1, but it gives you an idea of how the statistical test works. So there we've just scratched the surface of some statistics looking at differences versus relationships between two or more variables, and just a really brief overview of which tests to use.